Alright, now reflections and rotations in 2D. So this what was last video where we said we'll do part B and part C later. That will probably be in the next video because that's transformations followed by another transformation, but today's just going to be reflections and rotations in 2D. So as we already know, matrices can represent transformations, and types of transformations are enlargements, stretches, and also reflections and rotations. So here are 4 matrices. In GCSE Further Maths we have to know these matrices, and it's not just a job of like memorizing them because a reflection in the y-axis is -1 0 0 1, a reflection in the line y equals x is 0 1 1 0. How do we know it's specifically this? We don't have to like memorize them. You have to know them for GCSE Further Maths and for A-level Maths as well. You have to be able, A-level Further Maths, you have to be able to know them as well. But how do we like know this is the case? It all comes down to just do it graphically. So have our axes over here. Always start off with our base vectors. So here we have 1 0 0 1. Now if we reflect it in the y-axis, the transformation, if we just draw a pair of axes again, if we're reflecting this in the y-axis, well, this is just going to get reflected over here, and well, this is just invariant, that's just going to stay there. So that stays there as 0 1, and the 1 0 gets mapped to -1 0. So the matrix for this is -1 0 from our I vector or 1 0 vector being mapped over here, and then the 0 1 is invariant. So that is where this matrix comes from, because that's how all the matrices are derived, with the identity matrix or the base vectors I and j, or 1 0 and 0 1. We see what happens to them when we transform something, and the resulting matrix is the general matrix for that rotation or transformation. So you basically do the same thing. I'll do one more. Next I'll do, out of the bottom one, y equals -x. So we'll draw this. Start with that and that. That's 1 0 0 1. Now the line y equals -x is like this. Let's say like that. So when that's reflected in y equals -x, the transformation, well, this point over here, actually we'll start with this one. This one over here is going to go to here, so it's going to end up over there. So we'll draw it over here, and that point would be 0 -1. Because if that's 1 0, and if it's being reflected in y equals -x, well, that's just going to become -1 0. Because y equals -x, the x is 1 over here, so -x will be -1. And it's the same over here, so our j vector will be transformed over here to -1 0. And the matrix for this is 0 -1, -1 0. And that's the same thing. So we can derive these matrices just from starting here. So these are for reflections in basically lines. Reflection in the y-axis is the line x equals 0. Reflection in the x-axis is the line y equals 0. Now, for rotations, theta degrees anticlockwise. So we've got reflections, now rotations. If we want to rotate a point, how do we do that? Well, like always, let's start with our base vectors. One 0 0 1 over here. Now we want to rotate this, let's say a general theta degrees, and like you'll know from Argand diagrams, if we rotate something, the positive direction is anti-clockwise, negative directions is clockwise. So theta degrees, if it's positive, that's going to be anti-clockwise. So that's why it's theta degrees anticlockwise, and it's always about the origin. Linear transformations are always about the origin. The origin always stays invariant because that's like the starting point. Now, if we were to rotate this to here, so this will be our new point, and that's theta. And now if we were to do the same here, rotate it like that, theta degrees, both anticlockwise. Let's remove the arrows. So our new point is over here for the I vector, and our new point is over here for the j vector. Well, if we draw some triangles, so for this triangle over here, we've got it like this. That's the right angle. That's angle theta. Now, because the magnitude of the I vector is 1, and we're just rotating it, the hypotenuse is still 1, because this is like just the I vector that's just been rotated, so it's still got a magnitude of 1. Well, this over here is the x coordinate, and that's the y coordinate. Well, we can use some simple trigonometry to say the cosine of theta is equal to adjacent over hypotenuse, which is x over 1, which is just x, and by the same thing we get sine theta is equal to y. So writing this in a vector, xy is cosine theta, sine theta. Now for this triangle over here, we get this triangle where this is theta now, that's the right angle, and this is 1. Now this is x, but because it's going in this direction, this is where x is negative, so it's going to be like negative x, and then this is still y because it's still going like up here. So again, using trigonometry, cosine theta is equal to the adjacent over the hypotenuse, which is y this time, and the sine of theta is equal to the opposite over the hypotenuse, which is minus x. So now we get x is equal to minus sine theta. Now writing this as a vector, xy is going to be minus sine theta cos theta. So our transformation from 1, 0, 0, 1 is 1, 0 got mapped to this, so cosine theta, sine theta, and our 0, 1 got mapped to this, minus sine theta, cos theta. And that is the same matrix we have over here, cosine theta, sine theta, minus sine theta, cos theta. So that's for a general rotation, theta degrees anticlockwise. So we've now derived this, and the three main ones are these: 90 degrees anticlockwise, 90 degrees clockwise, and 90 degrees clockwise is 270 degrees anticlockwise. So if a question comes up saying 270 degrees, just know it's 90 degrees of the opposite direction. And then we've got 180 degrees, that doesn't matter whether it's anticlockwise or clockwise because it's going to end up at the same point. So now let's find the matrices for a rotation 90 degrees anticlockwise. Well, all we're going to do is, because it's anticlockwise, theta is going to be positive, so we can just plug in 90 to this matrix. We can just plug it into this matrix. So the cosine of 90 is 0, the sine of 90 is 1, minus sine 90 is minus 1, cos 90 is 0. So that is our matrix for a rotation 90 degrees anticlockwise. 90 degrees clockwise, well, like we said earlier, clockwise is the negative direction, so we're going to plug in minus 90. So cos of minus 90 degrees will be still 0. Sine of minus 90 this time will be minus 1. Minus sine of minus 90 will be minus 1, which is 1. And then again, cosine of minus 90 is just 0. And then 180 degrees, well, cosine of 180 degrees is minus 1. Sine of 180 degrees is 0, minus sine of 180 degrees is 0, cosine again of 180 degrees is minus 1. So these are our matrices for rotations 90 degrees clockwise and anticlockwise and 180 degrees, and these are our reflection matrices. Now let's do an exam question. So we've got this question over here, part A. Describe fully the single geometrical transformation U represented by the matrix A, and it's 3 marks. So we have to say 3 things. So first, we can see that these are trig exact values, half and root 3 over 2. So let's just write out our matrix, which is cosine theta, sine theta, minus sine theta, cos theta. So we'll just write cos, sine, minus sine, cos. Now, here and here, cos theta is equal to minus half. So solve for theta, arc cos of minus a half. And what we get is theta is equal, oh, I'm in radians, so that's 2 pi by 3 radians. You could leave your answer in radians or degrees, so I'm just going to leave mine in radians. 2 pi by 3 is 120 degrees, so you could write 120 degrees. And we'll just check it for sine theta, so let's just put 2 pi by 3 into minus sine theta, so minus sine of 2 pi by 3, and that should be minus root 3 over 2, and yep, that's minus root 3 over 2. So theta is 2 pi by 3. So describe fully the single geometrical transformation, 3 marks. So the first mark is going to be from saying it's a rotation, because we could either have a reflection or a stretch or a enlargement or something like that. So first mark is from saying rotation, I'm hoping. Second mark will be saying by how much, so 2 pi by 3 radians. And specify the direction, so it's positive, 2 pi by 3 is positive. It's not minus 2 pi by 3, so it's going to be anti-clockwise. And always about the origin. Okay, so that's part A. Part B. The transformation V represented by the 2 by 2 matrix B is a reflection in the line y equals minus x. Write down the matrix B. Okay, we could just look back and say, oh, y equals minus x, that's 0, minus 1, minus 1, 0, but you're not going to be able to do that in the exam. So you can either memorize that and say, oh, it's going to be 0, minus 1, minus 1, 0, or just derive it. So 1, 0, 0, 1, y equals minus x, reflect it. That's just going to go down to here, to minus 1, no, 0, minus 1, so 0, minus 1, and this is going to go down to here, to minus 1, 0. That's done. Now again, this is followed by, that's going to be in the next video, so we'll leave part C and part D for now, but let's just check the mark scheme for part A and part B. So part A, rotation is 1 mark, 120 degrees or 2 pi by 3 radians, yep. Anti-clockwise, yep, we got that. And allow from the origin or O for origin, yeah. So that's the 3 marks. So like I said, we get 1 mark for saying rotation, another mark for saying what theta is and anti-clockwise, and the 3rd mark for about the origin. And part B, 0, minus 1, minus 1, 0, yeah, that's correct. So yeah, we'll do one more question, because this is linking the determinant thing and this, and also knowledge of matrices. So part A, show that M is non-singular. Well, if a matrix is non-singular, the determinant is going to be non-zero. So basically, if M is non-singular, put a bit of dash there, then the determinant of M is not 0. And now we just have to show this. So the determinant of M is equal to AD minus BC, so 1 times 1, which is 1, minus root 3. Okay, so we're minusing minus root 3 times root 3, which is going to be minus 3, but minus minus 3, which is plus 3, which is 4. So 4 is not 0, therefore M is non-singular. Part B. The hexagon R is transformed to the hexagon S by the transformation represented by the matrix M. Given that the area of hexagon R is 5, find the area of hexagon S. Well, the transformation matrix is M, and the original hexagon, so the object, we'll just put area as A is equal to what? Oh no, it's 5. And the image area is what we have to find out. Well, we know that the determinant of M is the area scale factor. Now, because the object is transformed by M to get the image, the area is going to be scaled by this area scale factor. And the area scale factor, well, we just worked out as the determinant, which is 4. So the area of the image, or the area of hexagon S, is going to be 5 times 4 because we're scaling the area, so 20 units squared. And let's just check the mark scheme. So part A, yep, determinant is 4, and that's not equal to 0, so that makes it non-singular. And then yet the area is 20, so we got that correct. So next will be successive or transformations following one another. Hope this was helpful. Bye bye.